Okay, so it's our great pleasure today to have Amin Coja-Oghlan from Frankfurt, and he will talk to us about inference and random factor graphs. So please go ahead.
Right, thank you. So I would like to share with you some of my recent and recentish ideas and results about inference problems on random factor graphs. And as you can see from the slide, it's joint work with a lot of people that I've had the pleasure to work with over the last couple of years. And so actually this problem, or this family of problems, goes back quite a long time. For example, a lot of problems on random graphs, a lot of optimization and inference problems were studied already in the 80s and 90s. For example, there's some very important work by Ravi Bopanna from 1987 about the planted bisection model. So what you would do is you would take a set of vertices, a large set of vertices, and partition the vertices into two classes, red and blue, and then insert edges randomly so that edges between vertices of the same color are preferred. And then your objective would be to find the optimal bisection in this model, the bisection that cuts the least number of edges. Also, there's a very well-known work by Alon and Kahale from 1997 about the planted coloring problem. So here what you would do is you would take a set of vertices, assign them random colors, and then create a sparse random graph on this vertex set such that the colors that you predefined or prescribed for the vertices are a proper coloring of the resulting random graph. And then your objective would be to, given just the graph, to find any Q coloring of this graph. And also, of course, there's the notorious planted clique problem, where you take a uniformly random graph, GN1/2, and then single out a number of vertices and turn them into a clique. And the problem here would be to either outright identify the clique, either put your finger on where the clique is, or simply just distinguish the random graph with the planted clique from a purely random graph. And in a purely random graph, obviously, you would have a maximum clique of order log n typically. But interesting enough, in the planted model, we can't do much better than actually identifying the clique, the planted clique, once its size is as large as about square root n. And this result with the square root n order was already obtained by Alon, Krivelevich, and Sudakov in 1998. And all of these papers were actually very influential. And let me say up front that there's a vast literature on this family of problems. And I'm going to inevitably have to disappoint some of my friends and colleagues by not mentioning their favorite references. On the other hand, I think, I'm going to lose some favor and lose some friends maybe by giving this talk. On the other hand, I believe that as people give more talks on the subject, they also lose friends. So if you rescale by the decreasing partition function, my luck will improve over time again. Anyway, so let me just rumble on. In the 90s and early 2000s, the perspective on these problems was a bit different than it is now. At the time, we had some upcoming inapproximability results. People, for example, were very interested in approximation algorithms, and they were kind of disappointed to learn that, for example, you can't approximate the clique problem well or the chromatic number. And so these random graph problems were seen as a way out to some extent. So even though you cannot really hope to gauge algorithms meaningfully by looking at the approximation ratios they attain, maybe at least you can use these random models to benchmark algorithms to say this algorithm is better than the other. This technique, this algorithmic technique works because it does something clever on a random graph, or that sort of result. And also people were interested in these models in order to study heuristic methods. For example, the Alon-Kahale algorithm was based on spectral methods, which are very successful in many applications. And Alon and Kahale, to some extent, tried to find an explanation why these work in practice. And in fact, this work has had a lot of impact. So many papers went on and used similar techniques in the context of other problems. And finally, one other motivation was to foster new algorithmic ideas. For example, Bopana's work was one of the seminal works where semi-definite programming was used, and in the context of such graph optimization problems, even before the breakthrough Goemans and Williamson contribution. Of course, these days we come from a different perspective. Our interest is probably mostly in statistics and learning. And so we come from the viewpoint of inference from noisy observations. If we are presented with noisy data, what can we learn about the object of interest effectively? And one interesting way of looking at it that I learned from a paper by Lenka and Florent is the so-called teacher-student model. In this model, you imagine a teacher that is supposed to train a student by conveying a certain ground truth to the student. And the teacher finds themselves unable to just convey the ground truth verbatim, and instead presents the students with a number of noisy examples that are generated on the basis of the ground truth. And depending on the quality of the teacher, some of the examples might be very, might contain valuable information, others might be misleading. So the student faces the problem of figuring out on the basis of the examples that they are presented, what the ground truth was, or at least to recover as much of the ground truth as possible. So the student cannot get their hands directly on the information that the teacher tries to convey, but instead receives some noisy data and is supposed to learn the hidden information somewhat indirectly. And a good model, a good example of such a model is the stochastic block model that has received a lot of attention in recent years. This is a bit similar to the planted coloring model of Alon and Cajale, in that we begin by choosing colors for the vertices. So we fix maybe a number Q, maybe 3 of colors, and in the first step, we simply draw a color for each vertex independently. And in the second step, so this coloring would be the ground truth that the teacher effectively tries to convey. And in the second step, what we would do is we would create a random graph where the probability that two vertices are connected by an edge depends on whether they share the same color under this coloring sigma star from the first step. And there's two different versions of this model. In the disassociative version, we would discourage monochromatic edges, kind of like in the Alon-Cajale coloring model, where we outright forbid them. And in the assortative model, we would actually encourage monochromatic edges. And so in most of the talk, I'm going to focus on the disassociative version, where we create a graph like this here, where effectively on the diagonal blocks of the adjacency matrix, we expect the graph to be a bit sparser than on the off-diagonal pieces. And of course, now in this model, the question would be, can we somehow detect the ground truth from the observations that we make? And naturally, the larger the number of edges, the more the graph is going to reveal about the ground truth. So there's a trade-off here between the parameter beta and the number of edges that we are going to need in order to discover sigma star. So in the disassociative case, the larger beta and the larger the number of edges, the easier it should be to recover, or at least partially recover, sigma star. Another example is low density generator matrix codes. In this case, I mean, this is an example from coding theory, and it's maybe not surprising that coding theory would come up in this context. In this case, the ground truth is simply a sequence of n bits. And we are not shown this sequence of n bits verbatim, but instead what the teacher does is they form a code word by simply multiplying this message vector sigma star with the generator matrix of a code. And then the resulting code word gets sent across a noisy channel. And our job as a student is to recover the original message sigma star from the noisy observation that we receive, namely we receive the code word, but not actually the code word, but the code word plus some noise vector that was introduced by the channel. And of course, the noisier the channel, the harder it will be to recover sigma star. And also the larger the matrix A, the taller this code word Y becomes, the more rows the matrix A has, the easier it should be in principle to recover the ground truth. Yet another example that I like very much is group testing. In group testing, there's a large population. And this seemed a bit outlandish at the time when we started working on this, but imagine that a new virus befalls mankind. And all of a sudden it spreads, and you have the problem of detecting the infected individuals within your population. So there's a large population, a small fraction of it hopefully are infected with the virus. And in order to economize test resources, we do not just test every person individually, every person separately, but we conduct pooled tests where several people are grouped into one test, and the test result will come back positive if and only if one of the participants of that test group are infected. One or more participants are infected. And then we receive these pooled test results, and the objective would be to learn from these pooled results who the infected individuals would be. And so maybe superficially all of these problems look very different, and they may seem to require separate treatment, but actually there's a common core to them. There's a common way of looking at them, which is a kind of, it's a very powerful formalism that might look a bit scary at first, but it's not so hard after all. And this formalism is the formalism of random factor graphs. It's a bit indirect, but there's merits to looking at it in this slightly indirect manner. So instead of, in a straightforward fashion, defining an inference problem, what we are going to do is we are going to first put the omelette on the other side and define a null model. For example, in the case of the stochastic block model, the null model would be simply just the Erdős-Rényi random graph. So just a purely random graph with no planted coloring, no hidden structure whatsoever. You just throw in a bunch of random edges. And in general, for these general models, not just the stochastic block model, but also the error correcting codes and the group testing and whatnot, there's a generic way of doing it. So we would create, namely what we would do is we would create a random factor graph. A factor graph has two types of vertices. On the one side, variable nodes, x1 up to xn. And these variable nodes are supposed to represent the entries of the ground truth vector. So for example, in the group testing problem, these would be the patients. In the stochastic block model, these would be the vertices or the colors of the vertices that we try to learn. And these variable nodes range over some finite domain omega, for example, the colors in the stochastic block model. And they are represented by these round vertices up here. In addition, we have factor nodes A1 up to AM that represent the interactions or the observations that we make about these variable nodes. And each of these factor nodes comes with a weight function. This weight function takes as input the spins or the values assigned to the adjacent variables and spits out a non-negative weight how much effectively this corresponding factor node likes that value combination. And in this null model, we simply just connect these factor nodes and the variable nodes randomly. These weight functions can be random as well, so they need not be the same for all the different check nodes. Also, the degrees of the check nodes need not be the same. We would assume that there's some prior distribution on these weight functions, maybe. And as for the graph structure itself, you could either create a bipartite graph, for example, of Adolphini type, or you could create a graph with given degrees, or I mean, yeah, any other natural random graph model that you could come up with, perhaps. The important thing about this null model is that it doesn't have any particular structure. It's just more or less purely random. There might be some restrictions like degrees and so on, but as yet, there's no particular assignment for the variables that we have in mind. Based on just this information, namely the weight functions, essentially just the weight functions, we can then define a probability distribution for this null model on assignments. So for any assignment or configuration, any value assignment of the n variables, we would define the corresponding weight simply as the product on all the individual factor nodes of the weight that that factor node assigns to the values under this assignment. And this weight, I mean, this total weight then naturally defines a probability distribution where we say the probability that a specific configuration comes up is proportional to its overall weight. And there's a normalization required, of course, and this normalization quantity is what we call the partition function. Right, so any questions up to this point? I think I can somehow, maybe. Yeah, I can see the chat. So if you have any questions, if I'm going too quickly or something, just type it in the chat. I think I can, yeah, I can see it now. Okay, otherwise I'll just plow ahead. Okay, so we have this null model where we simply just basically link up variables and factor nodes randomly and choose weight functions for the different factor nodes. And so the interesting thing is that by looking at it in the right way, we actually obtain an inference problem from this model automatically. Namely, what we can do is we can define or introduce size bias distributions on graphs and on assignments. And to introduce the size bias distribution on graphs, what we do is we simply say, well, the probability that under this bias distribution, a specific graph comes up is proportional to the partition function of that graph. So the larger the partition function, the more likely it is for a specific graph to come up. And similarly for the assignments, for the configurations, we would say the larger the average weight of a specific configuration, the more likely we are to actually choose that configuration. So the weight of, so the probability of a configuration is proportional to its average weight. And also we can put these two things together, these two ideas together, and define the planted model for a specific configuration by saying that we draw a graph with a probability that is proportional to the weight of that particular configuration. Okay, so this way we already defined a planted model, and we have these two size biased distributions. And we can now generically define this teacher-student scheme. The teacher would go ahead and choose a ground truth sigma star from the size bias distribution on assignments. In most interesting cases, this will basically be the uniform distribution on assignments. There could be other cases where you might want to, where implicitly maybe this construction prescribes a specific weight, a specific Hamming weight on vectors or something. But in most cases, this will basically be the uniform distribution. And subsequently, the set of examples, the set of observations that the teacher produces is encoded by a random factor graph drawn from the corresponding planted model. So the teacher chooses first the ground truth sigma star and then produces the examples for the students, which are encoded in this random factor graph.
Amin, can I ask a question?
By all means.
So I should know this already by reading your papers, but so going, for instance, to the stochastic block model, and you just said, don't worry, it's basically the uniform distribution. But so, for instance, in the assortative stochastic block model, I take it that this distribution would be a little bit closer to having, a little bit farther from having equal size groups than the uniform distribution.
That's right.
Because we would gain from the overall probability, as you say, the average weight, from having more potential monochromatic edges.
That's right. So in order to encode the assortative model, you would have to take into account the non-edges, for example, or you would have to expressly forbid assignments that are very unbalanced.
And putting it differently, I guess this size biased prior, if you will, on sigma, I guess it has the property that if I choose from that, generate a planted graph from that, and then infer sigma, that the distribution on sigma is then a fixed point under that process of generation and then inferring it. Whereas the uniform distribution on labelings or colorings or whatever would not in fact be exactly.
That's right, yeah.
Okay.
Yeah, so that's one reason why I don't like the assortative model so much.
Well, okay, but so we could have said the same thing about the disassortative model, making it a bit closer to reducing the fluctuations in the
that's right.
the color class sizes.
That's right, but in that case, you would end up with something that is at least contiguous to the right distribution. Yeah, exactly. So that's a good point. But there's always ways of fixing this by introducing either non-edges or some other. Or for example, you could nudge it to some particular Hamming weight by having suitably chosen external fields. Okay, so right. So coming back to the teacher, so they just choose this ground truth sigma star and then produce the examples. And then the student is presented a set of examples, and their job is to basically get back at sigma star from these examples. And so the overall distribution that the student faces is simply just this reweighted distribution here from the first line. So basically, what we are looking at here is we have to figure out the posterior distribution of sigma star. That's the problem that the student has. In order to get back at the ground truth, they would have to get a handle on the posterior of sigma star. And so the nice feature about this posterior distribution is now something that I call the Nishimori identity, which is specifically that the posterior of sigma star is nothing but the Boltzmann distribution. So in other words, the student's problem is to get a handle on the Boltzmann distribution of this planted random graph G star. And in particular, a quantity that is of fundamental interest in this context is the mutual information, which is the information-theoretic potential that basically tells you how much you can learn about the ground truth. And this quantity is up to a constant related to the expectation of the logarithm of the partition function. So the amount of data that we can learn about the ground truth is effectively encoded in the partition function in these models. So having seen this general framework, which may look a bit abstract and a bit scary, let's see how we can get the peculiar models, or the models that I showed in the beginning from this. So for example, the this assortative stochastic block model we would get by saying, well, my variable nodes are just the vertices of my graph. I've got Q colors at my disposal, and I have a single weight function which takes as input 2 colors and says the weight is e to the minus beta if the colors are the same, and 1 if they are distinct. And the null model in this case would just be the Erdős-Rényi random graph. So if you follow the dots that I outlined about this abstract factor graph model, and you just basically run this procedure, you will arrive at the stochastic block model. The LDGM code you can also get from this construction in a fairly, it's a no-brainer basically. What you do is you take your n variables, it's convenient to encode the Boolean or the bit 0, 1 by plus minus ones. And you have these factor nodes that correspond to the parity checks of your error correcting code. In coding theory in particular, it's actually a good idea normally to be a bit diligent about the choices of the degrees. So you can sometimes get some mileage out of choosing the degree sequences on both the variable side and on the factor node side diligently. And so you can then basically, so for example, one construction that is very convenient is if you prescribe distributions on the variable node side and on the factor node side, and then draw IID samples from these distributions. And then you generate a random bipartite graph with these particular degrees. And these weight functions down here encode both the parity checks and the noise level of your channel. And also group testing you can encode easily. On the one side, you have the variables which represent the patients. On the other side, you have the factor nodes which represent the checks. And the weight functions basically just indicate whether the test result is compatible with the infection status that you surmise for the different patients. So the advantage of having this unified framework is, well, that we can actually prove things about it, and that we can obviously then just use this general result to get some information about particular problems of interest. So in particular, again, on the basis of physics predictions, there's a generic physics approach to these problems called the cavity method. And the cavity method tells you how you, for example, can compute the mutual information in these problems. So how can we compute this mutual information potential that tells us how much about the ground truth we can recover from the observations? And another question that comes up and that can be answered heuristically in this context is whether there's an information-theoretic threshold. In other words, whether there's some threshold, some signal-to-noise ratio effectively from where on you can start non-trivial inference if you are given infinite computational resources. So is there some point from where you can, in principle, learn the ground truth, at least partially from the data that you observe? And of course, the next question would be, can you actually perform this task efficiently? Is there some efficient algorithm for learning or getting a part of the ground truth back from the noisy data? And so, like I said, the cavity method is based on the belief propagation message passing scheme. One important hypothesis is that in these inference problems, you don't have complicated long-range correlations, namely that the posterior distribution, the Boltzmann distribution, effectively is what we call replica symmetric. This means that in a cartoon-like fashion, it either looks like this, that the support of your Boltzmann distribution is one big blob, which indicates that you have too little information, you can't do anything, you simply have not enough data to learn the ground truth. The second possibility is that it looks like this, that your measure decomposes into an abundance of little islands. One of these islands is inhabited by the ground truth of your problem, but unfortunately you don't know which. So in the absence of a lucky guess, you cannot get back at the ground truth in this scenario. And the last possibility is that effectively, basically, maybe up to trivial symmetries, there's just one blob in your measure. And this one little blob houses the ground truth, so it should be easy to get back at it. And generically, in replica symmetric problems, the physics recipe for dealing with them would be the belief propagation message passing scheme. Belief propagation basically associates two probability distributions with each edge of your factor graph. These are probability distributions on the set of colors, for example, in the stochastic block model, and generally on the set of values that your variables can take. And the belief propagation formalism sets out a bunch of equations that these variables, these messages, are supposed to satisfy. And the messages are essentially sufficient to get a full picture of what your Boltzmann distribution looks like. So the heuristic would be to basically try and find solutions to these fixed point equations here, and then follow the belief propagation formalism that you may have heard about, for example, in the context of tree factor graphs, to basically follow this formalism to get the information about the model that you need. And so maybe we are in luck, and maybe there's not so many fixed points to these equations, maybe not so many solutions to these equations. Maybe we can somehow find them, classify them, and get the information out that we want. In particular, the messages contain the information necessary to compute the mutual information in this model. Namely, there's a formula called the beta free energy that tells you how you can calculate your partition function. And what you should do is basically you should find the fixed point of belief propagation that maximizes the beta free energy. So this heuristic physics approach called the cavity method basically reduces your problem to the problem of finding the belief propagation fixed point that maximizes this functional. And in fact, there's one more step that you can take, namely this belief propagation, the system of equations here refers to a particular factor graph. Now, actually, our factor graphs are random and sparse, which means that locally they are described by some sort of a Gordon-Watson tree. So you could, instead of running belief propagation on the actual factor graph, you might as well replace the factor graph by the Gordon-Watson tree that mimics the local structure of your graph, and then work in terms of not the messages themselves, but in terms of the distributional messages that you would obtain on this Gordon-Watson tree if you were to kind of unravel this Gordon-Watson tree layer after layer. And so this results in a probability distribution on messages. In other words, in a probability distribution on probability distributions on values for your variables. And when you do this step of abstraction, what happens with the beta free energy is that it turns into a functional on the space of probability measures on messages. Anyway, this is all worked out beautifully in this article by Lenka and Florent from 2016. And this theorem here turns these ideas into rigorous maths to a large extent on a wide class of models. It's not totally universal. There's a bunch of interesting models that are not covered by this. And so writing down the assumptions to this theorem is a bit unpleasant. So I will not do it. I will just promise you that there's some symmetry assumptions and some mild assumptions on the degrees of your random factor graph model that suffice to turn these physics predictions into mathematical theorem, at least as far as the mutual information is concerned. These symmetry assumptions basically postulate that there must be a trivial fixed point to your belief propagation recurrence. For example, in the stochastic block model, this would be the fixed point where all the messages are the uniform distribution on colors. In other words, if you know nothing, then this should be a fixed point to your belief propagation equations. In the error correcting codes, for example, the symmetry assumption would be satisfied in the sense that all the messages uniform, meaning that I don't know any bit would be, again, a fixed point to your belief propagation recurrence. And there's also a sort of convexity condition that is satisfied by the disassortative stochastic block model, but not by the assortative version of the stochastic block model that is needed to make this work. Nonetheless, it's kind of, yeah, it's a step in the good direction, I would say. It's not, it doesn't cover everything, but it provides a, yeah, somewhat comprehensive justification of these cavity method predictions. And it seems fair to say that the techniques probably carry over to a bunch of other problems that are not formally covered by the result as such. So for the Erdős-Vényi model, we did this with Lenka and Florent and Will Perkins a few years ago. And more recently, some of my students, Max Hahn Klimroth, Philipp Leuk, my postdoc Noela Müller, Mattia Pasch from Munich, and Costa Panagiotou did it for more general models with prescribed degrees, for example. So we can obviously, now that we have this abstract result, we can plug in specific models. For example, this result here verifies the mutual information for the disassortative stochastic block model. The formula comes out as a variational problem. So you have this functional here, the beta free energy, functional on the space of probability measures on a simplex. And so in order to solve this problem here, you're supposed to find the probability measure on the simplex that maximizes this functional here. Of course, this is a bit complicated. In fact, it's probably awfully complicated if you try to solve it. But it matches the physics prediction, and at least it proves that these heuristic techniques actually get to the bottom of the problem. So it's pretty complicated, but it's not more complicated than predicted by the physics methods. And okay, at least it's replica symmetric. So in other words, you have at least some idea, I mean, what level of complexity you are facing. Right, so we can get so what goes wrong in the assortative model. So we can actually get the assortative model into our framework, but what happens is that there's a somewhat inconvenient convexity assumption that is needed for this general result, and that is simply violated by the assortative stochastic block model. We can get one direction out of our result. So one direction you can get, namely you can get the lower bound on the information theoretic threshold, but not the upper bound. Right, so there's a corollary about the information theoretic threshold in the stochastic block model. For two communities, this was already known, for example, by, this was already known thanks to Mossel, Niemann, and Sly. And there were bounds on more than two communities, and these results actually cover both the assortative and the disassortative. These results cover both the assortative and the disassortative version. Then we have a result about low density generator matrix codes. So again, this is just basically applying the general result to a specific model. And again, we obtain a result that matches the predictions from physics and actually proves a conjecture of Montanari from 2005, about the LDGM codes. Yeah, so I'm not going to say much about the proof, but basically it's pretty complicated, at least for this general result, but not because there's complicated computations. So the proof is not really heavy on computations. It's fairly conceptual in the sense that we use an abstract tool called the pinning lemma in order to verify this prediction that the Boltzmann distribution is replica symmetric. And then we use two, again, fairly conceptual, fairly abstract tools that are close in spirit to the physics calculations, namely the Eisenman-Sim-Star scheme and the interpolation method. The Eisenman-Sim-Star scheme is actually very, very close to the physics way of thinking about these problems, which is why I like it a lot. It gets a bit subtle because the coupling arguments required by this technique get pretty intricate or pretty delicate, but it's conceptually quite close to the idea of putting the physics calculations effectively on rigorous tracks. Right. Okay, so let's move on to algorithms. Right. So I'm going to.
I mean, a quick question.
Let's do it later. Yeah.
Okay.
Okay, so let's move on to algorithms. So the right. So again, a prediction from our good friends from physics is that actually belief propagation should be the ultimate inference algorithm. And so in these problems like the stochastic block model, for example, there's always a trivial fixed point that belief propagation could run into. Namely, in the case of the stochastic block model, just the paramagnetic solution where you say, well, everybody just has the uniform distribution, I don't know anything. And it is tempting to conjecture, and actually empirically it turns out that way, that the success of belief propagation as an inference algorithm depends on whether this fixed point is attractive or not. And so in other words, we would assume that so long as the fixed point, the trivial fixed point is attractive, it will trap belief propagation, and belief propagation will not manage to home in onto the non-trivial solution, onto the ground truth effectively. And that would mean that there might be a dichotomy in these problems between problems where the true solution to the information theoretic potential, the true maximizer of your beta free energy, branches out continuously from the trivial fixed point, or problems where it appears somewhere else at a totally different point discontinuously. And in the latter case, we would assume that maybe there's a gap between what you can do algorithmically and what you can do information theoretically with infinite computational resources. And there's actually a way of trying to formalize this, namely a generalized version of the Kesten-Stigum bound that again works for all of these factor graph models generically. And so here's how this works. So you would, for any given weight function, you would introduce an omega by omega matrix, a matrix on pairs of spins that kind of works like a transition matrix, which tells you how likely it is to transition from spin omega to spin omega prime under this particular weight function. And given a yeah, exactly. And given the, so Joe's answer is actually spot on. And given this, so that they are, okay, given this, given these matrices, these transition matrices here, you can then define an operator on the tensor space, R omega tensor R omega. And so this, I mean, if you know about the original Kasten-Stigom bound, this operator is kind of similar to describing the broadcasting process that you would see in combination with the reverse process. The reverse, I mean, the top-down process would be the first component of the tensor, and the bottom-up process would be the second component of this tensor, effectively. And on the basis of this linear operator, or in terms of the spectrum of this linear operator, we can then express the stability of the belief propagation fixed point. And so this particular threshold here, where you say, I look at the maximum eigenvalue of this operator in a certain constrained space where we throw out some eigenvalues that are irrelevant to our problem, then corresponds to a generic version of the Kasten-Stigom bound. So this would be precisely the point where the trivial belief propagation solution becomes unstable. So yeah, it would be tempting to conjecture that this is somehow related to the performance of belief propagation as an inference algorithm. And so in fact, if we specialize this to the stochastic block model, what we see is exactly, of course, I mean, by design, the original Kasten-Stigom bound, and there's matching algorithms for this by Amin and Sandon, even though we don't at this point know precisely how belief propagation, or rigorously how belief propagation will perform. If you look at LDGM codes, it turns out that in that case, this generalized Kasten-Stigom bound would be infinity. So this matrix here has a singularity, in other words. And this is unsurprising because in this case, the algorithmic version of the problem is closely related to the K-set refutation problem. And we don't expect that to be soluble for any finite constraint to variable ratio, I guess. So an open problem, I suppose, is whether generally we can algorithmically achieve this Kasten-Stigom bound. I mean, maybe there's some conceptual reason why that should always be possible. I think it would be very interesting to see that. And maybe conversely, it would be interesting, of course, to see negative results for specific types of algorithms failing below or up to this Kasten-Stigom bound. Right, so again, it would be interesting to refute or corroborate this hunch here that you would maybe get a hard phase in these inference problems, a hard algorithmic phase, if the Kasten-Stigom bound is separated from the information-theoretic bound, which typically occurs when this phase transition is discontinuous, when you get suddenly get a new fixed point, a new solution to belief propagation pop up somewhere at a place that is totally unrelated to the trivial fixed point. So let me finish by maybe saying a few words about group testing, which is a problem that I like a lot, because it's actually, I think it might even be useful, actually, which would be a new experience for me. I mean, working on something useful. And it's at the same time also quite intriguing. So in the group testing problem, at least in the version that is commonly studied in the math literature, the situation is this: you have a population of size n, and within this population, a certain number of patients, a number of individuals, n to the theta, are infected with a disease, with a virus, if you like, for some exponent theta between 0 and 1. So in this particular setup, it turns out that mathematically the interesting case is when the number of infected individuals is sublinear in the population size. And we conduct group tests, or we want to conduct group tests with as small a number of tests as possible in order to precisely identify the infected individuals. And a natural random design would be to simply have each individual join an equal number of test groups. And when you do a little back of the envelope calculation, you discover that the correct group size, the correct number of groups that each individual should join in order to extract the maximum amount of information should be about this much here. So something like n times log 2 divided by n to the theta divided by the total number of infected individuals. And as a result, you would discover that the number of the total number of patients per test would be something like n to the 1 minus theta times log 2. And in this case, okay, so in this case, it turns out that if you plot the infection density theta on this axis, and the obvious linear factor in front of the number of tests on this axis, that there's quite a large regime here, this red area, where the problem is information theoretically infeasible. So in this entire red area here, unfortunately, there's nothing you can do. So provably, it is not possible to actually infer the set of infected individuals correctly. On the other hand, here in this blue area, in this blue triangle, if you have, in other words, enough tests at your disposal, depending on the infection density, you can in fact solve the problem using simple greedy algorithms. So in that case, there are simple greedy algorithms that basically boil down to warning propagation will solve the problem in polynomial time. However, there remains a yellow area here where we can prove that the problem is information theoretically feasible, but at this point we do not know an efficient algorithm. Now, even though the group testing problem doesn't fall under this general theorem that I presented earlier, we can ask whether maybe something like a Kersten-Stigum bound, something like attractiveness of the trivial fixed point is going on in this case. And one of my students, Philip, actually worked this out a few days ago. And he discovered that actually there is some sort of fixed point attractiveness going on in this problem as well. Namely, if you are in this yellow area here, it turns out that, again, a trivial solution to belief propagation would be attractive. And even though the solution that you would find in the group testing problem would have a significant overlap with the correct set of infected individual, for example, because you can rest assured that anyone that is in a negative test actually is uninfected, there's still a trivial fixed point that pops up amongst the remaining individuals. And that will, and the stability of this fixed point will stop belief propagation from actually homing in on the correct solution. On the other hand, in the group testing problem, we showed that actually there is another solution to the problem. There's another construction, another random factor graph model that you can use in order to solve the problem precisely based on the idea of spatial coupling. So instead of using a plain random test design like I described in the beginning, what you would do is you would superimpose a geometric ring structure on your test design, partition your tests and individuals into compartments that are arranged in a ring topology, endow the seed, the beginning of the ring, with some extra tests so that you can get a good handle on the beginning, and then work your way from one compartment to the other, diagnosing the individuals along the ring topology effectively. And this idea of spatial coupling has, of course, been used previously in other problems, like, for example, LDPC decoding or compressed sensing, or also a variant of compressed sensing called quantitative group testing. And based on this idea, we can actually make this yellow area blue and obtain a group testing algorithm that solves the problem completely. And indeed, even though we didn't really set out in the beginning to analyze belief propagation, it turns out that this group testing algorithm that we came up with is precisely belief propagation. It's precisely a variant of belief propagation written down in terms of log likelihood ratios. So in this case, we can actually kind of close the book and say, well, okay, there's this Kasten-Stigum kind of behavior, and we can analyze belief propagation on the spatially coupled ensemble and prove that it completely solves the problem to optimality. Okay, so that's my last slide. It's a short summary. I try to explain or share my thoughts on these inference problems. I hope I didn't overwhelm you with the different models and this in particular this abstract model. I think there's a few interesting, potentially even practical applications, like maybe group testing. There's some unexpected applications of these results. Maybe, for example, we can get some results about the rank of random matrices that on the face of the problem don't seem to have anything to do with inference at all. And I should mention there's also an alternative approach to many of these problems based on the stochastic interpolation method developed by Barbier and Macris over the last couple of years. Thank you very much for your attention.
Okay, thank you so much for the talk. I guess there were a couple of questions already that came up during the...
Right. So, so about the pinning lemma. So this, yeah. Right. So, so this pinning trick is kind of a cute idea. And it doesn't work on inference problems alone. It actually works on any measure. So if you take any probability measure on, let's say, the Hamming cube 0, 1 to the n, and you draw a random configuration from it, and then you, from this random configuration, you fix a few bounded number of entries, and you fix these entries in your original model. So you basically fix a few randomly chosen variables in your original factor graph model to these particular spin values. It always works. It will always produce a replica symmetric problem. It will always make long-range correlations go away. So that's very funny. Right, so Andrea Montanari observed this in a particular case of error correcting codes in 2008, and then Raghavendra and Chan observed something like this in 2012 using a very short information-theoretic proof, and then we somehow discovered or rediscovered it in our language in the context of this problem as well. And at first glance, it seems pretty puzzling. So you might think, okay, if that's true, then why doesn't this entire idea of replica symmetry breaking collapse? But it turns out that it doesn't. So what Joe wrote in the chat is part of the answer. So obviously, if you only want to compute the free energy, then you only care about a constant fraction of the measure. That's certainly correct. But this would also be correct in the presence of replica symmetry breaking. So you might think that you could just basically steamroll replica symmetry breaking and always only work with replica symmetric problems. But that's not true. So the reason is that if you do this Eisenman-Sim-Star coupling construction, what would happen is that by adding some structure to your random factor graph, by doing this coupling argument, you would rescale the distribution that you have to pin from. So you would then have to go back and pin from a different distribution somehow. And that makes it very complicated. On the other hand, in these inference problems, this reweighting problem doesn't actually occur because you know a priori precisely in which way you have to do the reweighting, because that is encoded in this description of the model. Oh, yeah. Oh no. Go back all the way. So this is kind of encoded in this description of the model already. So yeah. Okay, so the next question. So the next question that I can see is when the physics predictions have been wrong. Yeah. Okay, so it depends on the definition of wrong. So, I mean, generally they have been more correct than wrong, I would say, overall. There's a few things that we could put our fingers on, where we could say, well, this was maybe a long shot and it didn't work. So one prediction that was wrong was, for example, about the performance of message passing algorithms on random constraint satisfaction problems. There are sometimes our good friends from physics were too optimistic. But I mean, that was a long shot to begin with, and they knew it was a long shot. Another example when they might sometimes be wrong is when these equations, these fixed point equations, have unexpected solutions. So at some point, somewhere, yeah, I wrote these fixed point equations. And sometimes they have a solution that you wouldn't expect, or that you would think they shouldn't have.
Am I the only one for whom the video froze?
No, you're not.
Also froze for me.
Amin, can you hear us? I'll try asking in the chat.
Hey.
Okay, there you are.
Yeah.
Sorry.
My computer just decided to crash.
Oh, okay.
It happens. So sometimes you get a funny solution that these fixed point equations shouldn't have, maybe, or you think they shouldn't have them, or you first think they shouldn't have them, then you think again, and then you discover the solution and you decide, well, actually that should be a solution. And so that kind of thing can happen, and that might lead to wrong predictions. So for example, in the case of these matrix rank problems, that was something that happened, that the yeah, I mean, the prediction just missed a fixed point. So yeah, but conceptually they've been surprisingly accurate, I would say. I don't know, but I guess there's other people also in the audience that could comment on this.
And Chris, did you have a question as well?
He answered it. Thank you.
Oh, okay. Are there other questions? Maybe while people are collecting their thoughts, I had a quick question, which was just this variational problem over pi for the beta free energy. Are there some natural conditions that help you choose the critical point?
Right, so I would actually assume, so I don't know. So an interesting thing that, an interesting question, I think, is whether we can narrow down the correct solution. And I think, in fact, we can. So in all the problems that I've worked on a bit more closely, what happened was that the correct solution was one of two things. Either the uniform distribution, just the trivial solution, or the solution that you would get if you were to start from the ground truth itself. And so, for example, and so obviously the, yeah, in some cases there's evidence that this is actually the only two possibilities. And of course it would be nice to prove that, because that would eliminate this crazy variational problem, or at least maybe not eliminate it, but at least turn it into something that you could manage on a computer.
Yeah. And do you know, for example, if in general the supervisor is always an attractive fixed point? It should be the case.
It should probably be the case, unless you're looking at some crazy critical values, maybe.
Oh, okay.
Yeah, I would think so, but we don't have a proof of it. Yeah. Actually, there's some funny cases. So, for example, one case that is really funny is when you look. Yeah, so this might be a counter. Could be a counter example. Actually, no. So it's probably not a counter example. But one case that is very peculiar is if you take a binomial random matrix. So an n by n matrix, every over F2, every entry is one with probability d over n. And so what happens in that case is that you get two maximizers at the same height. So you get two equivalent maximizers. And if you actually sample such a random matrix with probability half, the one maximizer is correct. And with probability half, it's the other maximizer.
I see. But then each of those would be an attractive fixed point, I see.
Each of them would be attractive, but you have two attractive guys that are precisely competing on the same footing.
I see.
So, sorry, just to clarify, you're not saying that the ground truth is an attractive fixed point. You mean that if you use the ground truth as an initial condition, you reach an attractive fixed point. So you would still have to do some dynamics from that point to see where you end up, right? But the conjecture, for instance, would be that wherever you do end up is, among other things, an upper bound on the overlap you can achieve. Indeed, that it would equal the overlap achieved information theoretically, right?
I mean, it would be interesting to investigate whether you can ever get anything else than, I mean, apart from maybe critical values, if you can ever get anything else but either the trivial solution or whatever you are getting when you start from the ground truth. I mean, I'm not aware of any specimen where you would end up with something else, but like I said, I mean, this is, we are talking about an infinite dimensional space, so there could be a lot of things hiding here or there. There's a lot of spaces to hide. Yeah. But
Any other questions?
yeah.
Oh yeah, just to follow up on your answer to my question. So I think you said that the performance of message passing on random CSPs, that was one case where physicists were too optimistic. Do you have a particular reference for this result, or?
Yeah, so there's a paper of mine from a few years back about belief propagation on random k-sub. So yeah, 2017. And so there were competing predictions about the performance of belief propagation guided decimation for finding solutions in random k-sub. And it's a bit unfair. So because I like physicists because they like to, I mean, they make progress. They are sometimes wrong and sometimes they change their minds. And I think that should be allowed. So I like people that change their minds. And so in this case, there was one prediction which was quite wrong. And then some of the authors changed their mind and the prediction was actually correct. So it's complicated. I mean, so in physics, so Chris might correct me, but my slant on the matter is that in physics, truth is a function of space-time.
In physics, it's considered just, it's better to say something wrong than to say nothing at all.
Yeah.
So, but I think part of the subtlety, right, is that from outside, physics produces a bunch of different kinds of results. Some of them might be numerical experiments on large but finite instances, which could produce incorrect extrapolations to infinity. Then there are things like, you know, analysis of message passing, which also uses numerics, like population dynamics, where you're not looking at, in theory, you're now analyzing infinite random problems, but you're using some finite precision for figuring out this, you know, this variational problem, this fixed point distribution of messages. And convergence can be very tricky to assess numerically there, and that can sometimes get something which is wrong, but it might be right that whatever that fixed point is would give the right prediction if we could compute it. So there's sort of different ontological statuses of different quote unquote physics predictions.
That's right. So another example where things, let's say, evolved over time is probably the hardcore model, right? And some other cases where people were not quite certain what the correct level of replica symmetry breaking should be. So I think hypergraph coloring also changed status at some point on that count.
I mean, if I may ask, you didn't mention Hettering, your sorry.
Right. Yes. So there was another point for debate, I guess.
Right. So his work was on survey propagation.
That's right.
And I believe it stopped at the same value where your analysis of the belief propagation stopped, right?
It was a bit higher, so he got this extra log k factor.
Yeah, but
yeah, but let's say yeah,
right.
So maybe some physicists expressed opinions about survey propagation that were slightly more upbeat than the result that he believed he got. I mean, I hope I hedged my bets sufficiently.
I think you did. There's a paper, I think 2016, on something called backtracking survey propagation.
Right.
Just not sure anybody analyzed backtracking version of it, but there it's pretty sort of solidly conjectured that it should work up to the condensation threshold.
But it's, like I said, I mean, this entire realm of algorithms, I mean, I'm kind of tasked to capacity when I try to understand replica symmetric problems. But if you try to look at something that has replica symmetry breaking and then go ahead and run an algorithm on it and then set one variable at a time, I mean, that, yeah, seems like a pretty dear shot to me. So I think it's genuinely just very difficult to say anything about it. And but I think in terms of these inference problems, we are on safer ground in some sense. So they are mathematically a lot easier than problems that have replica symmetry breaking of some level, to the extent that we can actually, I mean, thanks to this pinning trick, and I mean, mostly thanks to this pinning trick, we can actually get a good mathematical handle on them. So, of course, it would be interesting to get more information still, but sorry, but it would be, it's much nicer in some sense. So if there's any case where we should actually be able to say interesting things about algorithms, I would think it's rather in, it's more likely to be in inference problems than in these CSP problems. And even in that case, mathematically, we don't understand the performance of belief propagation well.
Yeah, if we have time for one more question, may I ask one more? Nike, it's up to you.
Oh, yeah, of course.
Well, so as you're alluding to, in inference problems, we know that there is no true replica symmetry breaking in the thermodynamic sense because of this Nishimori business. There is only, as the physicists say, dynamical replica symmetry breaking, whereas in problems that are not quite inference problems, I guess even the physicists themselves don't always have a clear opinion about whether there is merely one-step replica symmetry breaking or perhaps full replica symmetry breaking, like in KSAT at non-zero temperature. My understanding is that there's supposed to be at some point full replica symmetry breaking up there, even though for whatever reason at zero temperature KSAT, we know that there's only one-step replica symmetry breaking. So since, do you have any sense of the extent to which we might be able to prove that one step is enough for some class of problems which are not literally planted problems?
Yeah, I've got no idea, to be honest. I guess I'm the wrong person to ask this question. Yeah. I mean, so another question would be, of course, in inference problems. So maybe that's also something that is a bit more in the realm of the achievable in terms of realistic or reasonable effort. Would be what happens if you move away from the base optimal setting. So, for example, in the stochastic block model, you could ask what happens if you don't tune. I mean, if you look at the Boltzmann distribution of the planted model or of the stochastic block model, not with this particular beta, but with another beta. Right, and so what we would expect is, of course, that in one direction you remain replica symmetric. So if you make the temperature higher, you should remain replica symmetric, I suppose, or at least that yeah, I seem to remember that conjecture.
Yeah, whereas there's
the
some
other direction
numerical
could get a bit wild, and this is actually quite interesting because it's related to another question, which is how correct inference or how well map should do. Right, so on the stochastic block model, we would expect that maybe there's another phase transition where map starts to kick in. So you might expect that there's again a regime where if you do map, if you actually find the most likely solution, that should be orthogonal to the ground truth, or more or less orthogonal. Whereas from another point on, that should be strongly correlated with the ground truth. So this might be related. I don't know. I haven't really thought about it much, but it's you know, and I don't know if it would be interesting to anybody. But I mean, as a purely as a toy problem, it might be a cute thing to figure out.
Yeah, I guess a related question is I don't have a clear understanding of why zero temperature KSAT isn't full replica symmetry breaking, given that it isn't an inference model.
At zero temperature, it probably is full replica symmetry breaking for large enough alpha.
I would imagine.
But I mean KSAT, not oh, I see. You're saying,
so the KSAT threshold itself comes out as S1 or SB, but if you make it denser, of course.
I see.
Yeah, there is a paper by Panchenko, I think, linked doing interpolation from large alpha to mean field model, right?
Yeah, that's right.
I see. But presumably there are other constraint satisfaction problems where the threshold of satisfiability is in the RSB regime.
Yeah, for example, for max cut.
Thanks.
The threshold.
Yeah, all this hypergraph coloring, I think, is another.
Max cut doesn't have a threshold for satisfiability. Maybe I missed that.
Well, the max cut value, I guess.
Yeah.
Or also for independent sets for graphs of low degree. Should also be full RSB.
If we're all still here, can I ask something? This is related to Chris's comments. So about like whether the physicists agree whether a certain problem is one RSB or full RSB. Typically, so from what I understand is that you try to do the one RSB ansatz, and you try to see if it's stable or not towards higher degrees of replica symmetry breaking. And if it's unstable, you just say it's full replica symmetry breaking. I mean, it doesn't occur to you that it's perhaps 2 RSB or something like that. So there's a dichotomy. It seems that in natural problems, there is a dichotomy between 1 RSB and full RSB, and there's nothing in between. Are there anybody think of any natural conditions that one can put on a problem to say that it's either replica symmetric or 1 RSB, or other than that, it's full RSB, it's nothing in between?
Good question.
I don't know the answer. I think there is some example about a mixed p-spin model with some particular mixture, which is some finite level of RSB.
Yeah, it seems. Yeah, are you talking about some results of Tuka and probably also Coja-Oghlan, or I don't remember exactly.
I don't recall whose it is. Yeah.
But it seemed that the mixture was very handpicked. It was some very particular thing, but I don't know.
Yeah.
I don't know how generic it is. This is the point, I guess. Yeah.
Any other questions? Okay, thanks, Amin, so much for a great talk.
Yeah, thanks for having me. Thank you. Bye.